Welcome to This Explainer. Let's dive right into the awe-inspiring, completely invisible, yet absolutely massive world of nuclear chemistry. We're talking about taking the fundamental building blocks of the universe and manipulating them, breaking them apart, stitching them together. It releases literally unimaginable amounts of energy, and it shapes everything from the stars up in the sky to life-saving tech in your local hospital.
For centuries, ancient alchemists had this dream of turning cheap metals into gold. It sounded like pure magic. But what if I told you that changing the very fabric of matter, literally turning one element entirely into another, is actually a real thing? It's not magic, it's science, and we call it nuclear transmutation.
Here is the roadmap for our explainer. We'll hit modern alchemy and transmutation, fission and chain reactions, look inside a nuclear reactor, cover the power of fusion, and finally check out radioisotopes in modern medicine and everyday uses of radioactivity. Let's get to it.
Section 1. Modern Alchemy and Transmutation.
So, nuclear transmutation. It's basically the conversion of one nuclide, a specific type of atom, into another. This actually happens naturally all the time through radioactive decay, but we can totally force it to happen artificially too. Actually, the very first man-made nucleus was produced way back in 1919. Ernest Rutherford bombarded nitrogen atoms with high-speed alpha particles, and the result? He created stable oxygen and a proton. He literally proved that humanity could artificially synthesize brand new elements. But doing this today requires some seriously monumental engineering. Just look at the sheer scale of the 17-mile Large Hadron Collider tunnel at CERN. Down there, particles are boosted using these massive superconducting electromagnets and smashed together at nearly the speed of light, all just to uncover the fundamental building blocks of matter. It's wild.
Section 2. Fission and chain reactions.
Okay, so instead of combining particles to build heavy elements, what happens when we intentionally break heavy, unstable elements apart? That's nuclear fission. Let's walk through exactly how it works using uranium-235 as our prime example. First, a slow-moving neutron bumps into a fissionable U-235 nucleus. The nucleus absorbs that neutron and morphs into this incredibly unstable isotope, U-236. It just can't hold itself together, so it snaps, breaking apart into two smaller, more stable nuclei, like barium and krypton. And here's the kicker. That split releases 2 or 3 brand new neutrons plus a truly massive amount of energy.
And that right there elegantly explains why fission is such a powerhouse. Those 2 or 3 newly released neutrons, they don't just vanish. If you have enough fissionable material packed together, which we call reaching critical mass, those neutrons fly out and strike other U-235 atoms. They split, releasing more energy, more neutrons, and you get this exponential, self-sustaining chain reaction. It all starts from one single nucleus and just multiplies like wildfire.
The absolute crucial takeaway here is the sheer scale of the energy we're talking about. To put it into a real-world perspective for you, fissioning just one single kilogram of uranium-235 produces about 2.5 million times as much energy as burning a kilogram of coal. 2.5 million times! The gap between a standard chemical reaction, like burning coal, and a true nuclear reaction is just astronomically vast.
Section 3. Inside a nuclear reactor.
Now, raw, explosive power isn't exactly useful for turning on the lights in our homes. To safely turn this incredible force into usable electricity, we need extreme control. Any nuclear reactor needs at least 5 vital components. Obviously, you need the nuclear fuel itself. You need a nuclear moderator to slow the neutrons down so they actually get absorbed. You need a coolant to carry all that intense heat away to a boiler. You definitely need control rods. And lastly, a super robust shield and containment system, usually massive layers of steel and high-density concrete to protect the operators from radiation.
Think of the control rods in the core assemblies like the brakes of a car. How do we stop a chain reaction from just spiraling totally out of control? Well, we use materials like boron because they are fantastic at absorbing slow neutrons. If the reaction is running too hot, operators just drop the rods deeper into the core to soak up neutrons and basically hit the brakes on the fission rate. Need more power? You pull them out. It's a very precise mechanical way to literally control nuclear physics.
Section 4. The power of fusion.
So we've talked about splitting atoms, but what about mashing them together? Let's pivot to fusion, which is the exact same process powering the sun and every single star in the universe. Fusion converts very light nuclei like hydrogen into heavier ones like helium. The catch? The hurdle to actually kickstart thermonuclear fusion is absurdly high. You need temperatures of at least 15 million Kelvin. 15 million! You need that intense heat to give the nuclei enough kinetic energy to smash past their extremely strong repulsive forces. At those temps, molecules completely break apart into atoms, and atoms ionize into a superheated state of matter known as plasma.
So how on earth do you contain something at 15 million Kelvin without the reactor just instantly melting into a puddle? Well, scientists use intense magnetic fields. What you're seeing here is a scale model of the ITER tokamak reactor currently being built in France. That magnetic field effectively suspends the superheated plasma in midair, keeping it away from the walls. If we can actually sustain this star power on Earth, we are looking at an unprecedented, virtually limitless clean energy source.
Section 5. Radioisotopes in Modern Medicine.
All right, let's step away from massive reactors for a second and bring this down to Earth, focusing on the deeply personal applications of nuclear chemistry in human health. Reviewing the list of isotopes we have here, these act as biological tracers. Because they share the exact same chemical properties as stable isotopes, our bodies just process them like normal. But because they emit ionizing radiation, doctors can actively scan them. This radiation exposure is carefully tracked using units like sieverts or rads to make sure it's biologically safe. And notice those short half-lives? That's by design. The radiation stays active just long enough to get a good scan, but decays fast enough to avoid any permanent damage to healthy cells.
For instance, during a cardiac stress test, doctors might inject a tracer like thallium-201. That specific isotope naturally concentrates in healthy heart tissue. So as the patient exercises, a scanner is actually tracking the gamma radiation being emitted from inside their body. Unlike a standard X-ray that really only gives you a structural snapshot, these tracers use ionizing radiation to show doctors how the body is functioning in real time. It's a total game changer.
Section 6. Everyday uses of radioactivity.
Now, you might think you only run into nuclear chemistry in hospitals or high-tech labs, but these invisible forces are quietly working all around us every single day. We actually exploit the penetrating power of radiation for some pretty incredible industrial uses. On one hand, X-rays securely scan luggage at the airport. On the other, massive quantities of fresh produce are literally bombarded with radiation before hitting the grocery store. Why? Because unlike non-ionizing radiation, this ionizing radiation completely shreds the cellular DNA of the microorganisms that cause food to spoil. It's preserving the food by knocking out the bacteria, and it does it without cooking anything or making the food itself radioactive.
But honestly, my absolute favorite example brings this entire explainer right into your living room. Think about your typical household smoke detector. Inside that little plastic shell is a tiny speck of a synthetic transuranium element called americium-241. It sits in there continuously emitting alpha particles, which ionize the air between two little metal plates and create a steady, tiny electric current. When a fire starts, smoke particles drift into that chamber, block the flow of ions, and break the current. That tiny drop in electricity is the exact thing that triggers the alarm. So a literal piece of the nuclear age is watching over you while you sleep. How cool is that? We've seen how manipulating the nucleus can create entirely new elements, generate massive amounts of grid-powering energy, let us peer inside the beating human heart, and even sound the alarm during a fire. The transforming atom is just a massive testament to human curiosity and our drive to engineer the world around us. So, from powering the stars to saving our lives, what do you think the atom will unlock for us next? Thank you so much for joining me for this explainer, and keep questioning the invisible world around you.